What if I told you that before equations, before theories, before modern laboratories, science began with one simple question: how much does it weigh? On For Science Salah Lotfy channel, we are starting a new scientific journey into the history of measurement instruments. And we begin with the most fundamental tool of all: the scientific balance. From the ancient two-pan balance used in markets and temples to the balance that helped Antoine Lavoisier prove the law of conservation of mass. And, finally, to today's high-precision electronic balances that can measure micrograms and even nanograms. This is not just a story about an instrument, it is the story of how science learned to trust numbers instead of intuition, how accuracy replaced estimation, and how a simple act of comparison changed chemistry, physics, and every experimental science. In this episode, you will see how the idea of weighing was born, why balance design had to change, and how errors themselves drove technological evolution. If you want to understand how science became precise, this episode is your starting point. Stay with us on For Science Salah Lotfy channel, where instruments tell the hidden story of science.
Welcome to For Science Salah Lotfy channel, where global scientific research becomes clear and accessible.
هنا نحول الأبحاث العلمية العالمية إلى معرفة مبسطة مترجمة لك بلغتك.
Ici, la science est expliquée et traduite pour tous.
Ciencia clara, accesible y disponible en varios idiomas.
Wissenschaft, verständlich und mehrsprachig für jeden.
قناة For Science Salah Lotfy channel، العلم للجميع وبجميع اللغات. تابعنا لاكتشاف المزيد.
Before science had equations, before it had laboratories, before it even had numbers like we do today, there was one simple question humanity needed to answer: how much? I think about this every time I pick up something heavy or light. You don't need to understand math, or even words, to feel the difference between a heavy rock and a handful of feathers. The earliest scientists, really, just curious people, figured out quickly: you can compare, you can sense heaviness. So, why was weight the first language of science? It's simple. Weight is something you feel. Long before rulers, clocks, or thermometers, people were already weighing things: stones, grains, lumps of metal, trying to figure out what's equal, what's fair, and what's true. But here's the twist. In everyday life, we talk about weight, but science actually cares about mass. Weight depends on gravity. Mass is a property of matter itself. But for ancient people, that difference didn't matter yet. What mattered was comparison. And to compare, you needed a balance. This is why experimental science can't exist without a balance. You can observe, you can describe, but you can't prove anything until you measure it. And here's something wild. Before the balance lived in laboratories, it ruled somewhere even more powerful: justice. The same scale that weighed gold and grain became a symbol of fairness, of truth. So when you see the scales of justice, remember, it's a scientific instrument at heart. Different worlds, same principle: equality, comparison, objectivity. That's where science truly begins. If you're into this kind of scientific storytelling, hit subscribe and turn on notifications. Next time, we'll travel back thousands of years to the very first real balance and see how a simple idea changed the course of science. Let's keep going.
To understand how weighing truly began, we need to travel back thousands of years, long before laboratories, long before written science. The oldest known balance is the two-pan balance, and the earliest archaeological evidence comes from ancient Egypt and Mesopotamia. Wall carvings, papyrus illustrations, and excavated instruments show balances being used to weigh gold, grain, spices, and precious stones. These were not symbols, they were working scientific tools. At its core, the two-pan balance is beautifully simple: a horizontal beam, a central pivot, two identical pans. When the masses on both sides are equal, the beam becomes horizontal. This is not guesswork, this is physics. The balance works on a fundamental principle: the equality of moments, or in simple terms, equal mass at equal distance produces equilibrium. That is why the two pans had to be identical, same shape, same material, same distance from the pivot. Any asymmetry would introduce error, and error even then mattered. For the first time in history, humans were no longer asking, does this feel heavier? They were asking, is this equal? This was a radical shift. It marked the first attempt to separate quantity from sensation. However, the early balance had clear limitations. Air currents could disturb the beam. Friction at the pivot reduced sensitivity. Human eyesight determined when balance was achieved, and the accuracy depended heavily on the quality of the standard weights themselves. Two people using two different sets of weights could reach two different results. Yet despite these limitations, the two-pan balance achieved something extraordinary. It introduced the idea that nature can be compared objectively, that mass can be measured without relying on human perception. This simple instrument laid the foundation for trade, for fairness, and eventually for science itself. In the next part of this episode, we will see how the balance moved from markets and temples into the laboratory, and how that transition changed science forever.
For centuries, the balance belonged to the marketplace. It decided the price of grain, the value of gold, and the fairness of a transaction. But at some point, the balance crossed a critical boundary, from trade to science. And that transition changed everything. A market balance answers one question. Is this fair enough? A laboratory balance asks a different question. Is this true? In the marketplace, small errors could be tolerated. In science, they could not. This is where a new idea emerged, the idea of a standard sample. Instead of weighing objects in isolation, scientists began comparing them to known, reproducible references. This led to the development of standard weights. Objects with carefully defined masses made from stable materials and stored under controlled conditions. For the first time, a mass measured in one place could be meaningfully compared to a mass measured somewhere else. This was, honestly, revolutionary. It allowed experiments to be repeated, results to be verified, and knowledge to be shared. Early chemists relied on balances to study reactions, transformations, and mixtures. They noticed, that substances could change form, change appearance, change properties, yet the total mass remained constant. Physicists began to connect mass to motion, force, and matter itself. The balance was no longer just a tool. It became a witness to reactions you could not see, a witness to laws not yet named. Without standardized weighing, there could be no quantitative chemistry, no early physics, and, no experimental method as we know it today. In the next part of this episode, we will meet the scientist who turned the balance into a decisive instrument of proof, and used it to rewrite the very foundations of chemistry.
By the late 18th century, the balance had already left the marketplace and settled permanently inside the laboratory, but it was Antoine Lavoisier who transformed it from a measuring tool into an instrument of scientific proof. Lavoisier did something radical for his time. He trusted the balance more than appearances, more than tradition, and more than authority. In an era when combustion was explained by the imaginary phlogiston, Lavoisier asked a different question. What does the balance say? He weighed reactants before a reaction. He weighed products after the reaction. And again, the numbers told the same story. Nothing was lost. Nothing was created. Only transformed. From this simple observation emerged one of the most fundamental laws of science, the law of conservation of mass. Matter does not disappear. It does not appear from nothing. Its total mass remains constant. This was not philosophy. It was evidence. The balance had become a judge. Lavoisier's balance was itself a revolutionary device, highly sensitive, carefully calibrated, and protected from environmental disturbances. For the first time, chemical reactions were studied quantitatively, not descriptively. Color, flame, and odor were no longer enough. Numbers became mandatory. This is the moment chemistry changed forever. Chemistry began when weight became evidence instead of opinion. If you are enjoying this deep dive into how instruments shaped science, don't forget to subscribe to For Science Salah Lotfy channel, because every episode in this series reveals how a single device can redefine an entire field. In the next part, we will see how the pursuit of greater accuracy pushed the balance beyond its classical limits and led to the birth of the analytical balance.
Once chemistry became quantitative, the classical two-pan balance was no longer enough. Scientists were no longer weighing grams of grain or metal. They were weighing fractions of a gram, and soon, milligrams. At this scale, every small disturbance mattered. This is where the analytical balance was born. The key innovation was not complexity, it was geometry. The analytical balance used a shorter beam arm, which dramatically increased sensitivity. A tiny change in mass now produced a visible deflection. But higher sensitivity came at a cost. The balance became vulnerable, not to human error alone, but to the environment itself. Air currents, temperature gradients, even the heat from a human hand could alter a measurement. That is why the analytical balance was placed inside a glass enclosure. This glass box was not decoration, it was protection. Its purpose was simple: to isolate the balance from moving air and stabilize the surrounding atmosphere. This brings us to a critical scientific distinction. Sensitivity is not the same as accuracy. Sensitivity tells you how small a change the instrument can detect. Accuracy tells you how close the measurement is to the true value. An analytical balance can be extremely sensitive, yet inaccurate if environmental factors are not controlled. That is why, before every measurement, the doors of the balance are closed. Not for ritual, for physics. Closing the doors eliminates airflow. It allows temperature to equilibrate, and it gives the balance time to reach mechanical and thermal stability. At this point in history, we see a major shift in scientific thinking. Measurement was no longer just about the instrument. It was about the conditions surrounding it. The balance had taught scientists a new lesson. To measure matter precisely, you must first control the invisible forces around it. In the next part of this episode, we will see how these invisible effects, humidity, static electricity, and human contact, exposed the limits of mechanical balances and pushed science toward an electronic solution.
As measurements became more precise, scientists discovered something unexpected. The balance was no longer the main source of error. They were. At the analytical scale, errors did not come from broken instruments, but from hidden interactions between matter and its environment. The first of these was sample error. A substance may look solid and stable, yet it can gain or lose mass simply by standing in air. This leads us to humidity. Many materials absorb water molecules directly onto their surface. This phenomenon, surface adsorption, can change a mass reading by milligrams or even micrograms. Nothing was added intentionally, nothing was removed. And yet, the number changed. Then came an even stranger effect: static electricity. When certain materials are handled, they accumulate electric charge. That charge can attract or repel parts of the balance system, creating forces that mimic changes in mass. The balance responds faithfully, but to the wrong signal. This is why one strict rule emerged: never touch the balance with your bare hands. Not because of dirt, but because of heat, moisture, and charge. A human hand is not neutral. It is a source of disturbance. Each of these errors forced scientists to rethink balance design. Anti-static devices were introduced. Humidity control became standard. Sample handling tools replaced fingers. The lesson was profound. Errors were not failures. They were information. Each source of error revealed a physical interaction that had been ignored. And each revelation pushed the balance one step closer to perfection. In the next part of this episode, we will see how mechanical limits finally gave way, and how electricity replaced weights, ushering in the era of the electronic balance.
By the late 20th century, scientists had pushed mechanical balances to their absolute limits, sensitivity increased, and errors were controlled. But one problem remained unavoidable. Mechanics has limits: friction, wear, and aging components. These issues just couldn't be eliminated. To move forward, the balance had to abandon its oldest feature: weights themselves. This is where the electronic balance was born. In electronic systems, mass is no longer measured by comparison between two physical objects. Instead, it is translated into a signal. One of the earliest approaches used load cells. When a mass is placed on the balance, it causes a tiny deformation in a material. That deformation generates an electrical response, which can be measured and converted into mass. But for high-precision analytical balances, a more elegant solution emerged: electromagnetic force compensation. Here the sample's weight pulls downward, and an electromagnetic coil produces an opposing force upward. The system continuously adjusts the electric current until, well, perfect equilibrium is restored. And this is honestly the key scientific shift. The weight is no longer compared to another mass. Instead, it is balanced by an electric current. The value of that current, well, it actually becomes the measurement. This is why, readings became digital. Numbers are no longer read from a scale or a pointer. They are now calculated, displayed, and processed electronically. Digital output allowed automatic calibration, data logging, error correction, and of course, integration with computers. The balance was no longer a passive instrument, it became an active measuring system. If you appreciate how deep scientific ideas are hidden inside everyday laboratory tools, don't forget to subscribe to For Science Salah Lotfy channel, where we uncover how technology reshapes science, one instrument at a time. In the next part of this episode, we will look at the modern high-precision balance, and see why today's balances are not just accurate, but honestly, intelligent.
Today, the scientific balance has reached a level of precision that Lavoisier could only have dreamed of. Modern high-precision electronic balances can measure down to micrograms, even nanograms in specialized instruments. But how do they achieve this incredible accuracy? First, internal calibration. Each balance can adjust itself automatically, compensating for tiny environmental changes or aging components. No manual weights are needed for daily use. Second, vibration isolation. These balances are often mounted on specialized tables or platforms that prevent the slightest tremor from affecting the measurement. Even footsteps in the room can be filtered out. And third, the balance itself has become intelligent. It's no longer just a passive tool. Now, it monitors environmental factors, corrects for deviations, and even communicates measurements directly to computers or laboratory systems. This is a profound transformation. What once required careful observation, patience, and repetitive weighing is now, well, instant, automated, and incredibly precise. Yet the principle remains the same: comparison. Only now the comparison is not between two weights, but between a mass and an electrical force perfectly controlled. The balance is no longer just an instrument. It is a smart device, a guardian of accuracy, and a silent witness to countless experiments. Through these incredible advances, we see the journey of the balance from the market stalls of ancient civilizations to the cutting-edge laboratories of today. In the final part of this episode, we will reflect on what all these developments tell us about science itself, and why a simple instrument like the balance can teach us so much about precision, observation, and innovation.
I'm sure you've heard the news. Science is always changing. But when it comes to weighing, there's a constant thread. Let's uncover what's really stayed the same through the centuries. From the days of stone weights and two-pan balances, to the rise of electronic precision instruments, weighing has always come down to one simple thing: comparison. No matter the era or the tool, the goal is to measure one mass against another, whether it's a hunk of metal or an electric signal. The technology advanced, but the principle stayed rock solid. Why does this matter? Because the balance remains at the heart of every lab. Every experiment, every breakthrough, starts with a trusted measurement. The humble balance is the silent guardian of accuracy, a bridge from our intuition to scientific proof. But the story isn't over. Next time, we'll dive into the world of thermometers, discovering how measuring temperature transformed science just like weighing did. If you've enjoyed this journey, hit subscribe and turn on notifications for Science Salah Lotfy. Because every instrument has a story, and every story brings us closer to the wonder of science.